This video lesson on differentials is the second video lesson we've had from section 3.9. The first one was on tangent line approximations. So I'm going to label this one part 2. Okay. Now there is no sheet to go with this video lesson, so you will need to take notes in your binder. There is a TI-Nspire file, however, that goes with this video lesson. It's the same one that you were using on the previous video. As you can see, it's titled 3.9 Notes. We will start this video lesson by looking at page 4.1 of that TI-Nspire file. So go to that page and await instructions. To help get you warmed up, on this page 4.1 it should be, just want you to duplicate the graph that you see right here on this page. Alright, why don't you pause the video and give that a try. Hopefully you had some success. Of course, it's not hard to plug in x squared. Now if you want to use f1 of x, that's fine. So we'd have f1 of x is equal to x squared. And now to get the blue graph, we are going to need two things, right? We'll need the slope of this tangent line as well as the point that's on the line. Well, as far as the point that's on the line, let's see, I think we know that f1 of 1/2 is going to equal 1/4, so that gives us the point 1/2, 1/4. And to get the slope, well, since we are calculus students, we'll get f prime of x, and that is going to be 2x. So now we need f prime of 1/2, which we can see is just going to be 2 times 1/2, or a 1. And now we can write our tangent line equation as f2 of x to equal 1 times x minus 1/2, and then plus 1/4. Alright. So if you don't have that, make some corrections and you can have that on your screen. Now move on over to page 5.1 of your TI-Nspire file, and you will see this picture right here. And we're going to spend a little bit of time talking about this, analyzing what the different pieces are here. First of all, I would just have you focus on the red graph, okay, and notice that we have 2 points, one at c, f of c, and another one at c plus delta x, f of c plus delta x. And just focus also on the secant segment that goes between those 2 points. Now, if we want the slope between those 2 points on the graph, okay, or the slope of that secant segment, then we know we just need to subtract, the y coordinates from these 2 points and divide by the x coordinates, right? Get an average rate of change there. I'm going to write that up here. There we go. We've got, as you see, the difference in our y values right up here over the difference in our x values. Now, a quicker way to write that slope, of course, would be to say that it's simply delta y over delta x, right? Because delta y is the change in your y values, and delta x, of course, is what we would get if we took c plus delta x minus c, change in our x values. To make this a little clearer, let me draw in some braces. So delta x, of course, is that distance, and delta y is this distance here. Now, as we look at our blue tangent line, we can see it also, of course, contains the point CF of C. That's the point of tangent C. And it also has another point that's delta x units. If you go delta x units away along the x-axis, it also has a point that corresponds with that x coordinate c plus delta x. However, it's not the same point, as we see, as what's on the graph, right? So if we wanted to get the slope of our tangent line here, we wouldn't want to do delta y divided by delta x, right? That would be the wrong slope. So we're not going to use delta x and delta y, we're going to use dx and dy. Now dx is actually the same number as delta x, okay? Just keep that in mind. So we're going ahead by delta x units or dx units. But the difference in your y values, yes, is is now we're going to signify that is equal to dy. Alright, so I'm just going to write up here what our slope of our tangent line would be, which is just dy over dx instead of delta y over delta x. Now these values dy and dx are what we call differentials. And hopefully it's starting to make a little more sense why we use this notation to represent the slope or derivative of a function, okay? Because it literally does mean, you know, the difference in your y over difference in your x, but for your tangent line. Of course, using calculus notation, we would write that f prime of x is equal to dy dx. We've probably written that before. You're used to seeing that. Okay. Well, this will lead directly to our definition for what dy is, because all we have to do, of course, if we want to solve for dy, is simply multiply over to the other side by dx. We would have that f prime of x times dx is going to equal dy. Alright, so you'll see that on the next page. The definitions on this page here do need to get into your notes. We have definitions for differentials. Alright, so given a differentiable function, y equals f of x, we will define the differential of x, which we call dx, as being any non-zero real number. And you can just know that, you know, dx is basically the same thing as delta x. It's saying we're going to go ahead of this point by a certain number of units. That would be this point here, this point C. All right, and now the differential of y, which we call dy, is a little different. Okay, it is given by dy equals f prime of x times dx. Please keep in mind that dy is not the same thing as delta y, right? Here's delta y, and if we want to mark dy's length, I'll just draw in the blue segment, right? So they are not the same thing, even though delta x and dx are, right? Here's dx and delta x, they are the same length. You should keep in mind that you know, delta y, we've been working with that even through pre-calc and before, right? That's the change in your y values on a function, on the given function. But dy, that's going to be the change in your y values on your tangent line. All right, so that's what's new. Try to also get a quick sketch of these concepts, because if you have a mental picture of them, I think it does help. Let's now use those definitions to determine the actual values for dx and dy as well as delta y, given the example we had. So we've got our function f of x equals x squared, and we're going to go with that c value at 1/2, as you should probably recognize this picture here. And we're going to determine delta y, dx, and dy if delta x equals 1. Alright, well, of course, the easy one to determine is dx, right? Because if delta x equals 1, then dx also equals 1. Alright? Now, the next easiest one to determine is probably dy. You might recall from the definition that dy is simply equal to f prime of x times dx. Alright, well, that would mean that dy is equal to 2x, alright, times dx, and since we have that dx is 1, we can fill 1 in. Now, if we're talking about at the value c equal to 1/2, then we could plug that in for our x, and we would have that dy equals 2 times 1/2 times 1. So we have that dy also equals 1. And finally, of course, to get what delta y is, we just need to do, you know, f of, let's see, if we're starting at 1/2 and we move ahead by 1 unit, then we would need f of 1.5 minus f of 1/2. Now, let's see, that'd be f of 3/2 minus f of 1/2. So f of 3/2 is going to be 9/4, and f of 1/2 is 1/4. So it looks like we would get delta y. See, I never wrote delta y here. Delta y would just equal 8 over 4, or 2. We can see graphically what this means by just putting seeing that the slope of our secant segment would be 2 over 1, right? And the slope of our tangent line would be just 1 over 1. So the slope of our tangent line is simply 1, and the slope of our secant segment for the red graph is 2. And it definitely looks like it should be steeper. Now if you're looking at the graph and saying, well, this doesn't look like a slope of 1, well, keep in mind that the x-axis is elongated. It's this. In fact, it's you have to go twice the distance on the x-axis to cover basically the same unit as you would on the y-axis. So that's one reason why it doesn't look like this is a slope of 1, but it is. Now we return to the problem we had on the last video where we were trying to approximate the square root of 100.1. And we're going to this time use differentials to do that. So to do this problem using differentials, we need to think about what's the value that we already know for sure is on this curve. And of course, we know that the point 100, 10 is on the curve. Now if we were doing a tangent line, of course that would be our point of tangency. So with differentials, all we have to ask ourselves, okay, so how far ahead are we moving? In other words, what's our delta x or our dx, right? So delta x equals dx. And in this case, we know that that is equal to, it looks like 1/10, right? Okay, or 0.1. And rather than actually figure out the actual change, in other words, we're not trying to get delta y, okay? We're going to get dy instead. So we know, let's see, since our function is, we'll just call this f of x is equal to x to the 1/2. All right, and we also know that dy dx is equal to f prime of x. All right, so we know that dy dx equals 1/2 x to the negative 1/2, or in other words, dy dx equals 1 over 2 root x. Okay, so therefore dy equals 1 over 2 root x times dx. So that would mean in this case that dy would equal 1 over 2 times the square root of 100. Okay, that's the x value, whatever the anchor is, or point of tangency, that's our x value. And then times our dx, which is 1 over 10. All right, so what does that give us? Let's see, that'd be 1 over 20 times 1 over 10, so it's 1 over 200. Okay, this is multiplication, not subtraction right there. Okay, so that tells us what dy is. So what that means, of course, if we're at the point 110, all right, and we just increased, our dx went up to 100.1, then that's what this is telling us is we need our y value to go up by whatever dy is. So it's going to go up by 1 over 200, or 5 over 1,000. All right, so of course that would give us the point 100.1, comma 10.005, which I think was the estimate we had when we used the tangent line approximation. Now, it shouldn't be a surprise that we're getting the same thing, because we're basically doing the same math. It's just approaching it a little differently. Rather than actually getting the equation of the tangent line, we're just using the slope of our tangent line to help us figure out how far up do we need to go to get it. I will also point out that you might recall that the actual square root of 100.1 was something like 10.0049. So we can see, that we should be getting a number a little bit bigger for our estimate than what the curve would be giving us. Before we move to the next example, I just want to point out that once we found our dy, we had to then add that number to our y value. So, that was important in terms of getting our approximation. Of course, our approximation wasn't 0.005. We had to add that to the 10. We're going to see in our next example that it's going to be a little different. We just have to pay attention to the question. On page 241, let's take a look at number 35 here. They are telling us what the thickness of the shell is here, that it's 0.2 centimeters. Okay, in other words, kind of the width of the plastic that we're using here, or whatever the material is. And we want to approximate the volume of the shell. Okay, not the entire cylinder, what it can hold, but just what's the volume of the material, or the plastic that makes up the shell of this. Okay. Now, if we gave this problem to a geometry class, they would be able to actually determine the exact volume of the shell, is what they would be doing. And it wouldn't be all that hard. They would just, get the volume of the big cylinder. Okay, I'll say volume of the big, and that would be the one that's got a radius of 5 centimeters. And then subtract the volume of the small cylinder, and that would be the one that has a radius of 4.8 centimeters. Okay, and of course we could do the same thing, but what we're interested in doing is just approximating that volume by using differentials. Okay, and so our anchor will be the big cylinder that's got a volume of, a radius of 5 centimeters, and then we'll use the change in our radius. Okay, so in other words, we can tell that delta R, okay, is going to be 0.2. All right, that's the change in our radius. However, let's be careful here. Since we're starting at 5 and moving back to 4.8, delta R is actually negative 0.2. Okay, your deltas and your differentials can have directions in a sense. So of course that means that dr is equal to negative 0.2. All right, and of course what we're interested in, if you think about it, is the change. This is equal to delta V. Well, we're going to estimate that by determining dV. Okay, determine dV. If we get dV, then we've got a good estimate of what the volume of the plastic that makes up this cylindrical pipe is. So first of all, we should probably be figuring out what is our volume formula. Okay, so that way we can figure out what dV is. So let's see, volume of a cylinder, we know that would be the area of the base, right, times the height. And it looks like our height is pretty constant. That's 40 centimeters. Keep in mind our radius is not constant. It's changing, right? So we're going to need to use a variable there. But so volume is going to be area of our base, which is just pi r squared, all right? And then times the height, which is 40. So it looks like we have a formula of 40 pi times r squared. All right. And now we know that dV dr, okay, is going to equal V prime, or in this case it's going to end up being what, 80 pi times r. So therefore dV is simply going to be 80 pi times r times dr. Alright, so let's see, dV will equal 80 times pi. What's our r in this case? Well, our anchor for our r is the 5 centimeters, okay? And then our dr is negative, let's say negative 2/10 or negative 1/5, okay? So very quickly we can see that our dV is going to be negative 80 pi, right? Since our 5 cancels with our negative 1/5. So we now have an estimate for what the change in our volume would be to go from the big cylinder down to the small cylinder, and that's really all we needed. It's maybe a little curious that we have a negative answer, so we just need to remember, if we're approximating our volume, that the volume would be approximately equal to 80 pi, and in this case I believe it's centimeters cubed. Okay, so we're just using our dV giving it that way. All right, I'm going to go to a new slide, and let's just quickly check our answer and see how that compares to the actual answer. Up top here we have our approximation. We figured out dV was negative 80 pi, which translated into a volume of the shell being 80 pi centimeters cubed, and that is approximately 251.327 centimeters cubed. Now here's the work for the geometry student. They get the volume of the big minus the volume of the small, and they end up with 78.4 times pi centimeters cubed, or 246.3 centimeters cubed. So not too far off, and keep in mind we got this estimate with no calculator. Okay, we were able to do the math pretty quickly and easily, whereas here it definitely kind of took a calculator to square the 4.8 and do our computations. Now, had the problem read to estimate the volume of the smaller cylinder, the inside cylinder, then we would have taken our dV and subtracted that from the 1000 pi. Okay, we would have taken that negative 80 pi or subtracted 80 pi from the 1000 pi. All right, but that wasn't what the question asked us to do, so that's why we stopped and didn't do that. Just want to clarify on the instructions here for number 11. I know this problem is on your assignment. Maybe we can do number 12 real quickly. They say find the differential dy. What they really mean there is to write a formula for the differential dy of the given function. So it's very easy. We've done it a couple times here. You just first need to get with dy dx, right? And in this case, in number 12, of course, it would be what? 3 times 2/3 times x to the negative 1/3. Okay, so we would have dy dx is equal to, looks like we're going to end up with 2 over the cube root of x, right, or 2 over x to the 1/3. Okay, and then just to get dy, all we have to do is multiply over by dx. So I'll do cube root of x and then times dx. That's all they're looking for. So just to clarify what that means. Now, if you knew some numbers for dx and you knew what the x was, then you could plug them in and get some actual numbers. For number 31 of your homework assignment, there is a hint on the assignment sheet that says to refer to example 3 on page 237. If you read on down to the bottom of that page, it talks about, it uses the word relative error. And if you continue reading, you'll see that the term relative error actually means the same thing as the percent error, which is what they're asking for in this problem when you look at part A. The percent error really just refers to once you know dA, okay, that's an approximation for the error of the area of the square, then if you'll divide that by the total area of the square, that will give you your percent error. So in part A, they're going to give you ds. You can use that to get dA, and you can use that to get your percent error, or your relative error. In part B, you can actually see that they're turning this around. They're actually giving you the percent error in computing the area. They're saying it can't be more than 2.5%. So they're giving you the percent error, all right, for the area. Okay, this is for A. Now you can use that to figure out what dA is, and if you know dA, you can get ds. And you're not going to stop there, because now they want you, once you know what ds is, you should be able to come up with a percent error in measuring the sides. So you're going to take that and get the percent error, okay, for S. So that should help with number 31, and I think that's the only problem you really have to use percent error on. But so I thought it would be good to just touch on it real quickly. All right, that does it for this second video on section 3.9, dealing with differentials. So you'll probably be doing the combined assignment off the assignment sheet, and pay close attention to whether it wants you to use differentials or a tangent line to do your approximation.